Okay, so we're getting into Unit 7. Unit 7 is all about um, triangle sides and proportionalities of triangle sides and how they relate with angles. And starting with this, we're going to refresh your memory about the Pythagorean theorem. And remember, Pythagorean theorem all is related with a right triangle. Okay, so after this exercise, you should be able to understand the Pythagorean theorem and how it relates to the right sides of right triangles. Right, so here we're given two right triangles. They are identical, right, and often they're given the lengths of the right triangles and different variables, a, b, and c, or x, y, and z. In either case, the Pythagorean theorem is the same, just with different variables, right? I like to use x, y, and z because it relates more closely with the coordinate plane, because x is your left and your right, y is your up and your down, and then the combination of your x and your y is your z. And then if it's not on a coordinate plane, you can just have one leg and another leg as your A and B, which is like one of your legs touching the right angle, right, and then the leg not part of the right angle or opposite of the right angle is the hypotenuse, right? So that's the three parts of that triangle, right? It's your two legs, your A and your B, or your X and your Y, and those two legs combined make up the right angle, right? They're at a 90-degree angle when you're using the Pythagorean theorem. And then the third line segment of that triangle is going to be the longest, and that is called the hypotenuse. Right, that's called the hypotenuse. Right, so Z or C here are the hypotenuse. Okay, so this is the leg, and then the hypotenuse for short. Okay, so either way here, you can solve these. If you're going to solve for C, A, or B, here's different ways to do it. You can say that your C here is C squared equals A squared plus B squared. That's Pythagorean's theorem. And your hypotenuse, the square of your hypotenuse equals the square of your two legs, the sum of the square of your two legs. That is the Pythagorean theorem. If you're going to solve for C or Z here, it would just be the square of A and B of the sum, and the square of X and Y. But that's not necessarily always how you want to do it algebraically, right? If you wanted to solve for A here, you'd rearrange. Let's say it's A squared, right, or X squared. Right? You would want to rearrange it first, and you'd say it's going to be C squared minus B squared, right? And this would be Z squared minus Y squared, and that should be intuitive, right? Because Z is your longest leg, and C is your longest leg, and you can't, if you subtracted, if this was backwards, and you subtracted something larger and something smaller, you'd have a negative result, and that's not going to make any sense, right? So if you were going to solve for A here, A equals the square root of C minus B, and X equals the square root of Z minus Y, right? But you might not want to go all the way this far when you're solving. You might want to, depending on what you're given, you might want to start up in here. Same thing with here, right? If you're going to solve for B, this is going to be your C, your hypotenuse squared minus your A value squared, and then you would solve for you could go all the way and say that it's going to be the square root of a c minus a. And then here, it is going to be the square root of this here. The square root of this, of your y value, is going to be equal to, algebraically, equal to your hypotenuse, which is your z squared minus your x value squared. This is just rearranging the equation, and if you put a radical on both sides of it, that's a really ugly radical. It's a really ugly radical there. Then I'll fix that. Right, and you could fall all the way through and say your y value equals your z minus x, but that might not help you to go that far and plug and chug. And you might, well, maybe we'll see that in some of these examples that we drew up here in a second. Okay, so these are the different forms that can help you to figure out all these different things here. All right, so let's go ahead and look at an example, and let's start with this one here. Okay, so we have the right triangle, and here's B, right? Okay, so this must be A, right? And then this must be Z. Okay, so we're trying to find B, right? So we know that Z squared equals A squared plus B squared, right? So we're going to solve for B, so we're going to say B squared equals Z squared minus A squared. Right, well, let's go ahead and plug in some stuff here because we have square roots of some numbers, right? So that wouldn't help us to put them inside the radicals already because that could get messy, right? So we're going to say B squared is equal to Z squared, so it's going to be the square root of 26 squared, right, minus the square root of 8 squared. Okay, well, if we say b squared equals the square root of 26, let's see what happens if I do the 26 square root and I square it. Hey, look, I got 26, and that algebraically makes sense. So if I have something inside of the square root and I square it, that's just going to be 26 minus 8. And then if I do 26 minus 8, I get 18. So B is going to be equal to the square root of 18. Well, can I break down the square root of 18 at all? Are there any perfect squares inside of 18? Well, there are. This is the square root of 2 and 9. Right? 9's a perfect. It has a 2 is a 3 times 3. That's a square root of 3 in there. So I can extract 3 from this. So B equals the 3 times the square root of 2. Right? So there we go. If you don't understand this here, like this was 18, and I took the square root of both sides, right here. So I ended up with B equals B squared equals 18. Right? So here, I need, in order from here to here, right, I kind of skipped a step there. So in order to get from here to here, I needed to square both sides and take the square root of both sides to clear the square. I got B equals the square root of 18, and then I could break down that into 2 times 9. 9 is the perfect square. Take the perfect square out of the square of the radical, and it turns into 3. So when I take the square root in, it turns into 9. Take it out, it turns into 3. That's how radicals work. Okay, so that's how. So this would be 3 square root of 2. Right. So remember, that's just a number. Okay, and I mean 8 could be 2 square root of because 8 is 2 times 4. So you could bring that out, and that would have been of the radical. So that could have been 2 square root of 2. So you could have said A here is 2 square root of 2. 2 square root of 2. But it was easier. They gave you 8 square root of 8 because it would have been easier to do it that way for the math. But anyway, so that's cool. Alright, so let's do this one here now. This guy right here. Okay, we're finding finding c. Now this is the hypotenuse, right? This is the leg. This is the leg. This is a, b, and c, right? So c squared equals a squared plus b squared. So this is easy. But we're finding the exact solution. And oh, you can't see that. We're finding the exact solution, and we're finding the approximate answer. Okay, so one's asking for the exact solution in mathematical terms, and then one's asking for, approximates, and we'll round it to the nearest hundredth. So 2 decimal points, right? So we'll say c squared equals a squared. A is 10 square root of 10 squared plus square root of 40 squared equals, right, so that's going to be c squared equals 10 plus 40 equals 50, right? So I'm going to have to say, and so I need to take the square root of both sides, so c equals the square root of 50, right? So can I break down that? Well, 2 times 50 is, or 2 divided by 50 is 25, and 25 is a perfect root, so that equals square root of 2 times 25, right? And that's going to be equal to, pull the perfect root out, that's going to be 5 times the square root of 2. Right, so the exact solution is 5 times the square root of 2. Right? But what is the, because that is, if I do square root of 2 times 5, I mean, that goes off the calculator forever. The approximate answer is 7.071. We'll do the thousandths, right? So that's the approximate answer. Right? This is much more precise. This is, if I multiply this, right, 7.071, and I multiplied that by, like, let's say 3216. Okay, it would give me that number, right? And then if I did, it's how do I store that in the memory? Let's see, memory. We'll put it like, it's 22740.336. Okay, now let me do it and go 5, or 2 times the square root, whoops, 2 square root times 5 equals, and I multiply it by 3216. I am off by, a couple of about, let's see, minus 22740.336. I'm off by 0.21808, right? So that's not exactly the same. So that's rounding errors and stuff like that. So as you can see, rounding errors in action right there. Okay. All right. So now we're gonna find the length of SR. This is this one. RS, SR, whatever. Given these two here, right? So this could be X, this could be Y, and this could be Z. Okay, and we'll round to the nearest thousandths. That's zero. That's hundredths. That's tenths, hundredths, thousandths. So that's 3 decimal points. So I need to find Y, right? I'm just going to use this guy right here. Right, so Y is going to be equal to the square root of Z minus X. Okay, so I'm going to go 48 minus 28 equals, and we'll take the square root of that, and Y is going to be equal to 4.472. There's my answer. That was pretty quick. Okay. Wait a minute. That doesn't seem right. Let's see. Let's see what happened there. 48. I'm supposed to square them. That's the problem. 48 squared. These should be squared inside of here. These should be squared inside of here. Okay, there we go. So 48 squared minus 28 squared equals, we'll take the square root of that, and now that should be, so SR, or our Y value, should equal about 38.987, the nearest thousandths. Yeah, that's more correct. That makes more sense, right? So if you do something and it doesn't make sense, right, make sure you're checking. I didn't necessarily do the write down the algebra correctly over here. All right. So here's the here is two triangles. We have TWK. So let me grab my trusty straight edge out. We have triangle TWK, which from henceforth will be known as triangle green. TWK is triangle green. Triangle green. And we'll have triangle burgundy, which is THK. Is THK. THK. These two triangles, like this. And well, maybe you can notice that they both share TK. But and they both have 90-degree angles, but that's about it. And TK is square root of 113. Okay. It tells me that TW is the square root of 45. TH is the square root of 68. And we're gonna find HK. And we gotta find WK. Okay, so this isn't too bad, right? They're both legs, right? Because we have the hypotenuse, because square root of 113 is the hypotenuse. So we can call both of these A if we want to, right? So we'll just say here that we'll say A for this one equals z squared minus b squared, and we'll say A for that one equals square root of z squared minus b squared, right? So for this one it's going to be square root of 113 squared minus square root of 68 squared. Actually, let's make it a little bit. Let's make it a little bit easier. Let's do it side by side here. A squared equals, because they're in radicals, A squared equals, or z squared equals z squared minus b squared equals minus b squared. Okay, that's the way we're going to do this, instead of putting in the radicals right away, because we have radicals to deal with. Alright, so for this one, both of our z squareds are square root of 113 squared. It's going to be equal to square root of 113 squared. Right, they both share 113. Okay. Now the only difference is that burgundy triangle here, HK, is, we got to figure that out. This is what we're going to call A for this one. So A squared, and then we're going to use square root of 68 squared. Over here we're going to use square root of 45 squared. Okay, so this math is going to be square root of 113 squared is 113, minus square root of 68 squared is 68. So 113 minus 68 equals 45. Let's square that. Square root of 45, it says we're round to the nearest thousandths. Alright, so A equals 6.708. That's the nearest thousandths. Over here is 113 minus 45. 113 minus 45, and that's the square root of 68. It's going to be A equals 8.246. So same concept there. Skipped a step. I just squared the radical and subtracted the things inside of there, and then took the square root. Alright, so that's what happens in here. Okay, so last thing with here is to introduce you to what we're going to call the sides of these triangles here. Okay, we're going to start naming names of these triangles, sides of these triangles relative to an angle. And in geometry and trigonometry, the reference angle we use a term in a Greek letter called theta. I don't know why they use theta. They've just been using theta for a long time. Okay, so if we're using this as the reference, instead of saying like angle A or angle B, right, we just say angle theta. Okay, so over here, this is angle theta, and down here, this is angle theta. So these are the different reference angles for these two triangles. Okay, different reference angles. This one's the top angle. This down here, this one, the reference angle is the bottom angle. Okay, so focusing on this triangle for now, right? Referencing angle theta, there are 3 sides in reference to theta. Right? The first one is the opposite side. Opposite. Okay? So it's the one opposite of theta. The next one is adjacent. ADJ for short. OPP for short. Okay? And then the last one is hypotenuse. Hypotenuse. HYP for short. Okay? So we kind of talked about this over here. Right? There's 2 legs, the opposite leg, the adjacent leg, and then the hypotenuse is always going to be the one that's opposite the 90-degree angle. Right? If we're talking about this one, right, the hypotenuse is going to be the same one. Right? But the opposite and adjacent are changing, right? Because now this one is the opposite, and this one is the adjacent. Because it's relative to the reference angle, because we're talking about this angle, because this one is now adjacent and this one is opposite, right? adjacent, and opposite. Okay, so those are some terms that you need to know for the next lesson. All right, I hope this helps out, and there are some things in the practice lesson that should help you master these concepts. All right, moving on to the next one.